speaking on it, but he's letting me do it, and he did a lot of work. But together we wanted to provide some information on what we do over there. The problem in Los Angeles is too many people and not enough water. Through the past 100 years, the population growth has been close to 6,000% increase. And with that use, of course, came a lot of water demand. But LA is dry. We only get about 15 inches of rain a year. If you were here in December, you saw an awful lot of it coming down really fast. And we got a lot of calls from the public saying the drought's over, right? Because of all the rain that came in December. But actually, we've only had 12 inches out of 15, so even though December was very wet, a lot of it just ran off to the ocean because it exceeded the recharge collection capacity. La Nina seems to be kicking in, and it's been dry most of January. And so we're actually 40% below normal for January. So it still is dry. We get our rain events in big dumps at one time or another, and we don't have a lot of rain, so it's challenging to supply water for that growing population. Most of our rivers, they don't look like Northern California rivers or the Pacific Northwest rivers. They're just a sewage effluent when water is flowing into them, or they're just bone dry most of the time. So how do we get the water to meet those needs? As you've heard, most of our water comes in from Metropolitan Water District, through the canals and aqueducts from Northern California and the Colorado River. That's the majority of the water. A good chunk of the supply is made up from local groundwater wells. There's over 300 wells in the Central Basin that all the different cities operate, Los Angeles, Long Beach, Cerritos, Downey, Lakewood, etc. They all pump out groundwater from the aquifers. But there's just not enough groundwater to meet the needs. And recycled water has been used for nearly 50 years as a groundwater recharge source. Fortunately, a long time ago, they figured out we could put that secondary and later tertiary water into the ground, and it was a great alternative supply for groundwater recharge. So I'm focusing in on the central groundwater basin here in LA County. It's got over 2.5 million people in it, and the area is about 270 square miles, separated by the Newport-Inglewood fault zone. And looking at a geological map of the area, it's mostly filled with sands and silts that have been folded and faulted due to Newport-Inglewood and other faults in the region. And looking at a cross-section from north to south through the central basin, you can see that the aquifers are sitting on top of a complicated bedrock that's been folded and faulted and is actually the source for all the oil that we have out here in LA. There's all this structure and the ancient marine sediments with the oil. But the aquifers are kind of smeared up on top and layered in the upper 3,000 feet overlying this bedrock. And this is what's being tapped for the different groundwater uses. As I mentioned, there's about over 300 production wells in the basin, and collectively pumping out around 200,000 acre feet per year. This map shows where all those little wells are located. The history of the groundwater levels in the central basin is a history of overuse and overdraft, severe overdraft. From the 1930s to the 1960s, water levels were dropping almost 10 feet per year. 10 feet per year in some cases. Loss of groundwater supply, wells were going dry, and along the coast it drew the seawater in, contaminated the aquifers with seawater intrusion. And if left unchecked, groundwater basins would have been effectively destroyed, unusable. So 3 solutions went into place in the late 1950s and early 1960s. The first one was to reduce the pumping through a court adjudication. It was wildcat pumping, and there were no controls, so the court stepped in and limited the amount of pumping that could occur in the central basin to 217,000 some change acre feet per year. But that's still greater than the natural safe yield. So they created our agency, the Water Replenishment District of Southern California. And our job, really, we're in a special district that was voted into existence to just find other water other than rainwater to try to stick into the ground and make up the overdraft. So part of my job is to calculate every year what the storage deficit is, and then try to find the water to stick into the ground. Historically, it's been imported water and recycled water to make up the overdraft. And then lastly, LA County went in and installed barrier wells along the coast. And to this day, they're injecting 24 hours a day fresh water and highly treated recycled water to help stop the seawater intrusion down in the Long Beach area. So where most of the water, though, goes into the ground for recharge, artificial recharge, is up in a portion called the Montebello Forebay. It's a region of unconfined aquifers where the aquifers at 1,000 feet deep are actually connected to the aquifers at 0 feet at the ground surface. So the rest of the basin is a series of aquitards and confined, but up in the Montebello Forebay, all of the aquifers are merged, and that promotes groundwater recharge to all the usable aquifers. A little cartoon sketch showing that concept of how recharge basins, you dig a hole into the sand and fill it full of water, and that water just flows down and can get into all the different aquifers. As you go further towards the coast, you start getting this layered system, and you have the confined aquifers, and you would not be able to go into the city of Long Beach, for example, and dig a hole out here and have any effective recharge getting down to the lower aquifers. But we're lucky, we've got this Forebay region, and it's actually pretty common in some of the coastal aquifers in the area. And in the Montebello Forebay, there's 2 spreading facilities. One is the Rio Hondo spreading grounds, and one is the San Gabriel spreading grounds. And we've heard a little bit about these at the session so far. They are owned and operated by Los Angeles County Department of Public Works. The Rio Hondo has 20 separate ponds, about 10 feet deep, and about 430 acres with 400 cubic feet per second of infiltration rate capacity, or a little over 900, or about 800 acre feet per day. They can put in about 3,700 acre feet at one time into storage. San Gabriel spreading grounds a mile away, that has 3 ponds, plus the river channel itself is soft bottom, and the water can just soak into the river bottom if you can stop the water from flowing. So this is what the basins typically look like. There's a procedure that LA County does to groom the basins and remove the silt and get them prepared for recharge water. And then the waters can turn on and start entering the facility. And then this is what it looks like on a good day when it's filled with either storm water, imported water, or recycled water. The amount of water that goes into these facilities currently is around 54,000 acre feet per year of storm water is able to be captured. We've got about 50,000 so far this year with those December rains, but we're still actually short of an average amount. Imported river water, imported river water from Colorado and from Northern California is around 21,000 acre feet per year. And then the recycled tertiary wastewater is currently 50,000 acre feet per year. And basically my story is that this water is becoming less available. This water hasn't been available since May 2007, the imported water. So over 3 years of lack of this supply. And we're having to buy more expensive imported water. And so to mitigate that, we're looking at ways to capture more stormwater to increase this number, to balance the overdraft in the basin. Historically, since 1938, 2.9 million acre feet of stormwater has gone into the ground at these facilities. And also, since 1953, it was the first year for imported water, also 2.9 million acre feet has been purchased to fill up the aquifers there. And recycled water since 1962 is about 1.5 million acre feet, so a tremendous amount of water. 7.3 million acre feet so far has gone into just these 2 spreading facilities to help replace the extracted groundwater. And as a result of that, you can see from the water level hydrograph that water levels almost immediately rebounded back in 1960 when the pumping adjudications took effect and the replenishment districts started putting in water. You can see the big rebound. And right now we're pretty happy with where water levels are. We don't want them to come back up to the historic highs because we had the flowing artesian wells and other problems which we don't want to reactivate. So our current challenge is the loss of the imported water that we typically have bought, and that's, you've been told, that's been due to drought conditions up in Northern California, environmental factors with the Delta smelt, and judicial decisions. We're having to right now, since we can't buy the cheaper, I say cheaper in quotes, because if we could buy cheap water, it would be $495 an acre foot. That's the imported water price that we pay for surplus water. But we can't buy that now, so now we're buying the $638 per acre foot. That's what we buy through the member agency to Metropolitan Water District. And we have to buy about 21,000 acre feet a year of that. So we try to find other sources to offset that imported need. So more recycled water is a big project we're looking at, as well as conservation to reduce the overall demand for water supply, and then more stormwater capture as another attractive alternative, which we are working towards getting more of that water. So one of the ways to get more stormwater is to temporarily dam up the rivers. I know a lot of the environmental folks don't like damming up rivers, but these are inflatable rubber dams. Have historically been manufactured by the Bridgestone company near Firestone, in inner tubes, tires and such. And it's just a big piece of rubber that can be filled up full of air and laid across the river channel and inflated when there's storm water. And it dams up the river, and that slows the water down, and the water then just soaks into the permeable soft bottom sediments. We built two new dams in 2008 with the Los Angeles County Department of Public Works and on the San Gabriel River to help capture more stormwater. And the cost of this thing was $4.2 million, so like $2.1 million per dam. They're not cheap. And then we have to deal with some kind of, sometimes there's vandalism, burning fires at the base of them or shooting them. So there's different strategies to try to prevent that. But they capture about 3,600 more acre feet per year of stormwater. So really, these things pay for themselves in 2 years, considering the amount of price of imported water that we're buying right now. So a very effective means of creating groundwater recharge of stormwater. The next thing that we're doing is there's a Whittier Narrows Dam is at the northern end of our service area, and that was built for flood control by the Army Corps of Engineers in 1957. What that does is it fills up with water, and the Army Corps holds that water until the downstream spreading grounds drain. And then once those spreading grounds are drained, the Army Corps releases the dam water, and it gets to the spreading grounds. But there are oil wells, oil production going on in that same area that looks like it's wet right now. And because those oil wells were there, we couldn't have the conservation pool full of water very high. So the oil wells were in our way. So in a rare success, we were actually able to buy out with LA County the oil wells and have them move out of that area. And that allowed us to fill up the conservation pool with more water. Oops, there's the wrong button. Excuse me a second. They were planning on using those oil wells anyways. I think if they were really heavy producers, it would have been tough to buy out the oil wells. We were talking earlier about having to get to a slide. So buying out the oil wells, filling up the conservation pool has allowed 3,000 acre feet a year more water to be recharged into the Central Basin. The third thing that we're doing right now is constructing a brand new pipeline with Los Angeles County. Nothing too crazy about it, other than for the first time, we're going to have a connection between those two spreading facilities. Just a pipeline down an existing street. It's a 78-inch diameter pipeline. Here's pieces of the pipe that are going to be trenched and laid in the ground over here. It's going to be finished in March of this year. And then that just allows us flexibility to move water from one spreading ground to the next. The problem right now is when one spreading ground was full, but the other one wasn't, the full basin would just have to waste the water and lose the water. So now we'll be able to transfer water from the full one to the less full one and balance them both out as if they were one facility. It goes by gravity one direction or pumps to pump it up the other direction. So that will allow us to increase stormwater capture by 1,300 acre feet per year. And the cost of that pipeline is $7.6 million. It'll take a little longer for the payback, but 10 years or so. Fourth thing that we're looking at to capture more stormwater is to lower the Vadose zone. We need more Vadose zone. Right now, during big storm events, beneath the two spreading grounds, the Vadose zone rises to near the pond bottom. Normally it's down at 30 feet or so, but during heavy storm events, the mounding builds up, and that causes the percolation rate to go down considerably, and you lose the rest of the stormwater. It just flows down to the ocean. So there's plans being looked at to install production wells in the area and suck down, pump out the groundwater, lower the Vadose zone, and then that frees up more space for more stormwater capture. All that water that's pumped out would be piped and served to drinking water users downstream, so they wouldn't have to operate their wells anymore. They can use these wells. These things would run all year round. And just create deeper Vadose zone, get more stormwater in there. And the modeling we showed, if you pump out 24,000 acre-feet of water, you can get 17,000 more acre-feet of stormwater. So just a tremendous amount of stormwater can be induced just by creating a steeper Vadose zone, preventing that mound from getting too close to the ponds. And then finally, when we don't have spreading grounds to deal with, we go out and look at other parts of the groundwater basin. And so we're looking at a lot of low-impact developments, or LIDs type projects. Heard of these? These are mechanisms to get rid of the surface runoff after rain events into the ground at your facility, or even a residential home, instead of having that water run to the storm drains and get to the ocean, picking up greases and oils and all that. There's concern over water quality and such. So designing ways to get the stormwater into the ground at your site will greatly assist in groundwater recharge. Of course, your soils need to perk. You need to have good geology. You need to have good ability to put the water in. But we've identified quite a few areas through modeling, land use analysis, GIS surveys, and some pilot studies to get that water into the ground. Bioswales is one technology, which with really nice porous pavements. Dry wells, rain harvesting, and smart landscaping are some of them. And one project has recently been completed through the LA and San Gabriel Rivers Watershed Council. It's on Elmer Street. And they just dug up the street. They laid gravel in the bottom. They laid collection pipelines and mechanisms that these pipes have holes in them, and the water then will just go down into the street, underneath the street, and that way it will collect all the rainwater on that one street, and it will just soak into the ground instead of it running off. And this is what it looked like afterwards with the street. So in summary, imported water for managed aquifer recharge in the Central Basin is becoming more challenging. It's more expensive and it's less reliable, but we still have to fill up the aquifers. So one solution is to try to get smarter with the stormwater conservation through innovative projects. And I described a few of the projects here with new pipelines and conservation pools and rubber dams, lids. All those things are being looked at just to try to capture more rainwater. So with that, I'd like to answer any questions. Thank you very much.
Yeah, we got time for a couple questions. Jordan?
Have you considered removing some of the line portion of the Rio Hondo and operating that like the San Gabriel River Dam?
Yeah, we've looked at it. It hasn't been proven too favorable to unline the concrete channels. The Army Corps owns and operates those, and there has been an area of rising water and shallow water in the northern part of the Rio Hondo, and by removing those, we'd have to do a lot more pumping to lower the Vadose zone there, I think. Removing the concrete is tough. We've been looking at the LA River, which is concrete the whole way. Try to remove that and promote recharge. But in order to remove the sleek superhighway of drainage for storm events, you would need to widen the channel quite a bit for flood control, and that land just isn't available. So in order to maintain the flood protection on the Rio Hondo, we're going to need to keep the path of the concrete channel.
Any others? Andy?
Your Vadose zone production, spreading grounds, and the 6-month travel time, how could you resolve the use of recycled water recharge and setting all over the models?
Yeah, good question. These wells would be located outside of the 6-month zone. There'd actually be more like around a 2-year travel time. My cartoon showed them really close, but actually they're about a half a mile away from the spreading grounds and sort of the center line between the two spreading grounds. So they would not, they would far exceed the 6-month travel time. Brian, I promise they would.
Any others? Yeah,
Is there a concern that the pollutants such as
stormwater are not good for the aquifer, or we're comfortable that the filtering that goes through the earth into the aquifer is sufficient to remove those?
Yeah, that's a terrific question because we're all concerned about what's in the surface water. All of the studies that have been done on this project and the previous ones show that the Mother Earth does a terrific job at cleaning up and filtering and polishing the water, the geopurification. We're not seeing anything related to the surface water runoff getting down there. We've been putting stormwater into the ground since 1938. So that's 70 years of stormwater going in and monitoring those all over the place, and we just don't see any problem at all with it. And then for those specific lid projects in residential neighborhoods and such, this water augmentation study that we were participating in took a look at water quality impacts through small beta zones and dosimeters and shallow monitoring wells, and just didn't see any negative water quality impact due to the percolating turbine runoff, which is great.
Great. Thank you, Ted. If you have any more questions, you can pop them out.